Hello everyone, my name is Roy Jafari and I would like to welcome you to another video of data mining series. In this video, we're going to start learning about the classification algorithms KNN or K-Nearest Neighbors. This is one of the most simple and perhaps very effective algorithms for classification task of data mining. We're going to learn about what this algorithm is, how it works, its strength and shortcomings, and also we are going to look at how we can actually implement this using R in this very video. Alright, let's look at the slides. Alright, so in this video, of course, like any other video, we're going to start with some recap, some concept that we've been developing in the previous videos. We're going to quickly go over them, and then we're starting to learn what is KNN. And then we'll talk about its flaws and advantages, and then also we'll talk about how we go about setting K, which by that point you know what K is. And then also we're going to, just in this video, implement everything in R and start enjoying working with KNN. Of course, we're going to do that using example. So KNN is a classification algorithm. As we saw and talked about, classification is basically determining the class or category of a data object based on its attributes. In other terms, as we said, classification tries to find the relationship between the independent attributes and the dependent attribute when the dependent attribute is categorical, right? So KNN has a very specific way of connecting these, sort of like finding this relationship, and that's basically what we are going to learn in this video, KNN. So we are going to learn how KNN does this. So KNN is a classification algorithm, and it is known as a lazy learner. The reason is KNN does not actually take the time to find these relationships. Whenever it is asked of KNN to predict something or classify something, it just starts in that moment to go find some analogy in the data to come to a classification. So that's why it's known as lazy learner. And once we learn some eager learner, which is eager versus lazy, you'll exactly know what we mean by lazy learner. So this is the flowchart of the KNN algorithm. So let's go through this flowchart together using this example. All right, imagine we have a three-dimensional data. We've got X here, we've got Y here, right? So this is X, this is Y. These are our independent attributes, and this is our dependent attribute, right? So the class is our dependent attribute. So here we want to apply K and N on this data and see how it works for us, right? So first we decide K. This is our data set, and we have to input the value of K. So we decide K is going to be 4, and then we input the new data, the data object that we want to know its class. So this is something that we're interested to know. We want to find that based on this data set we already have. So we are trying to predict the class of this new data, and we do see that this new data is here based on its X and Y, or its independent attribute. Then we find the K-nearest neighbors to this point, right? So the K-nearest neighbors are these 4 data objects, right? And then we say, is there a consensus? Meaning that most of the classes of the data objects that are neighbors to this data object are of one class. And we do see that there is a 3-to-1 consensus. In this example, 3-to-1, therefore there is a consensus. So we decide that yes, there is a consensus, and then we assign, pay attention, we assign red to this class as well. So KNN, as simple as that. That's how KNN algorithm works. It's a very simple algorithm. I mean, as far as understanding it, being able to actually code all of this requires some levels of programming. But the good thing is, and in this video, we're going to use either R or Python. So we're not going to be doing the program. We're just going to use modules that have already done those programs. Let's look at another example that makes this a little bit more challenging. What if, when we get to the point that we want to check about the consensus, there is no consensus? I mean, do you see here we've got 2 greens and 2 reds. How do we do this? Then we have to run the tiebreaker, right? We have to run the tiebreaker. And running the tiebreaker could be in different ways. I mean, one of them, it could be completely random. We say, just do it randomly. There is no indication from the data, just do it randomly. Or it says, okay, now find the ones that is the nearest. And you would say, okay, the nearest is 2, so there is going to be red. And then it says, find the smallest index. This one is a little bit weird because there is no rhyme or reason why this would make sense. I think it's sort of like the same as random, but in this case the smallest index is 1, therefore it's going to be red again. And then it also, another way is to do a weighted selection, right? Doing a weighted selection means is that if the data object is closer to if the neighbor is closer to this data object, have more weight for the data object, right? So because 1 and 2, which are red, are closer than 3 and 4, therefore they would have more say in which one of what's going to be the class of this data object. Therefore, since 1 and 2 that are red are closer than 3 and 4, even in this one is going to be red. So that's how we would break the tie, and it depends on who has coded it. I think most of the packages go with this weighted selection, but some packages such as MATLAB, I know that it uses the smallest index, which is kind of weird, but anyway. Once we figured it out, then we assigned that red. So that was that example. So now that we understand KNN, we have to also start understanding its weaknesses and its strength. Its weakness is the fact that if you have a large data set, meaning you have a lot of data objects and in many dimensions, every time you have to find the class of a new data object, you have to do a complete search of your whole data set. And that's not a very scalable solution, because if you've got a big data, every time you do a search, and the search has to be repeated again and again and again. And that's not very robust or scalable. And that's why a lazy learner is not advantageous in this situation, because you've got a big data. You have to do this all over again every time. So there are 2 ways this can be fixed. One of them is that to do some pre-sorting. If you are familiar with databases, one of the ways that the databases makes it easier for applications to find the records that they need, because it's a huge amount of data, is to sort of like resorting and assigning indices based on those sorting, right? So something similar could be done for the data objects. So the sorting could be easier. Another possible solution would be to sort of let go of and exact answers and settle for the partial distance calculations. For example, you could decide that a few of the attributes are more important. So let me say, for example, this is our big data, and you've got these many attributes, right? You've got 5 attributes. You say, okay, these 2 attributes are more important, or they have more variation across the data, right? And then you say, okay, let me find some candidates across my data object based on only these two attributes. And then once I have those, then once I have those candidates, or I have removed the ones that have no chance, now I engage all of my attributes. So that's another possible fix. Like I said, it's not exact, but if the data objects are, your data set is too big and you are insisting on using KNN, this could be an approach. So next we talk about how do we go about setting K. The way that the hyperparameters of any data mining algorithm is done is most of the time by computational tuning. K is a hyperparameter of KNN, and basically we experiment with different Ks across different subsets of our data, and we figure out what is the best K. So if you remember, for K-fold cross-validation, right? So here K is equal to 4. We could do something like this. We could, test different K for these train set. Let's say I'm going to test K from 1 to 10, and then again do the same thing. K 1 to 10. And again do these, and then across all of these experimentation find an average of the performance of different Ks, and the one K that has the best performance is the one that you would choose, right? So that's basically how you would go about tuning or setting the hyperparameters of a data mining algorithm. Again, coding this would be very difficult. You don't have to do it. We're going to be using modules. In this very video, you're going to see how that's done. Anyway, so let's look at an example. So in this example, we've got a data set with 3 attributes. 2 of them are independent, and 1 of them is dependent attribute. So we want to find this relationship using KNN. Actually, as we said, sort of KNN does not really find any relationship. It just sort of like for each, because it's a lazy learner, for each new data object we are interested in knowing its class, it goes and finds this relationship for that specific data. All right, so let's do this in R. R here. Okay, so before you start, you have to let this run, and these are to install some packages and then call those packages. This might actually take a while, at least going to take 10 minutes, and the way your console is still working is that there's going to be a sort of like a stop, like red sign right here. So if you see a red sign here, then it's still working. Once that's done, then you can start running these codes. So the first thing we're going to do, we're going to read our data. So if I run this, my data is red, and this is the same data as we saw in the PowerPoint slides. So this is the data. I've got income, score, default, and of course default binary. We're not going to be using this, default binary, because KNN is a classification algorithm. We can work with these categories. But one thing we do need to do, because KNN uses the distance between data objects, as we discussed, distance calculation is a very important aspect of that. We need to standardize, actually normalize income and score, and we use the function scale to get that done. So we do that. We say, I want to scale the income and score. So once I run that, the df norm, so let me show that to you here. So the df norm is going to only have the standardized income and score, but we're still going to need the other attribute, which is the dependent attribute. So I'm actually not going to need this, so I'm just going to remove this from here. So now I have to sort of like attach these two together, so my df norm has that one as well. So I run this. Now I see that my df norm has income, score, and default, right? But you know, if you see the name is like df.default, I mean, let's just change the name. And by running that, so this is sort of like extra now, so I'm going to delete this. By running this line of code, this is going to be done. So I run this, and now df norm, you know, has this as default. So that's it. So next we want to create some partition, like, you know, split our data into train and test set. And we're going to use create data partition, which does this splitting randomly. For us to you know, be able to have randomization at the same time, get the same result, you know, you, me, you know, wherever you use this set.seed3, it means that you are making sure that the randomization is going to be the same for you and for me. If you have used the sklearn module in Python, random state, it's similar to random state idea there. So basically when you run this, now if you run this function which uses randomization, you're going to get the same result. So these are my you know, random sample that I'm going to be using. I'm using like p as 55, meaning that my train set, I want to be 55% of the data. So this is my randomized index. So once I use that in my df norm, my train set is going to have 12 rows and 12 out of 16. And when I do it for the test set, I put negative sign here, means like everything that is not here, it's not there. So now I get the test set, and these are my test set, right? I split data into train set and test set. So now I'm ready to start doing my experimentation. So I create my you know, cross validation by using train control. You know, this is just the way it's done in R. I mean, it's a very specific line of code to write, but this is how R work. You know, this is what you would need to write for this to work out. That's all I can tell you about this. So you run this, you specify you want to like do cross validation with k equal to 2, and you again change your, you know, random state. You know, you don't have to do this, but for us to make sure that this is done, you know, for you and me are the same thing, and because this once you engage try control is going to do this randomly, we set this so we will get the same result. So we do this, and then we train for different k from 1 to 6, and our metrics is accuracy. And then once we say KNN fit, now it tells us that the best k is 6. You know, the average accuracy for KNN 6 was the best one, and of course for kappa as well. The difference between accuracy and kappa is sort of adjusted to account for the you know, imbalance nature of some data sets, and you know, because this data set is not imbalanced, it's balanced, therefore, you know, accuracy is as good, it's good, right? And you know, we do actually have a better metric for imbalanced data sets that we have learned about, which is FS score. But anyway, that's beside the point. We know our k, and we've you know, trained our KNN. So once we train our KNN, now it's time to test it, right? So we test it using the function predict, and the fit KNN that we have, we get the prediction for our test set, and these are the predictions: yes, yes, no, yes, 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 yes. So these are our prediction. We create a confusion matrix. This is our prediction, this is our actual data, and we have to specify what is our positive you know, class, which is yes in the case of yes here. So we call confusion matrix, And if you scroll up here, you will see that our confusion matrix is here. We've got 4 correct yes yes, 2 correct no no, and we've got 2 let's see, we've got 2 false positive, no false negative. And our accuracy is 0.75, right? So that's our accuracy for our prediction. And another things we can learn here is that we don't have to just get the class. We can actually calculate the probability, right? So here, instead of just predicting, we can pass type as prob. This will output the probability values for us. So once we run this, now it gives us the probability of yes and no, right? This is the probability of yes is 50%, for this case 50%. And if you pay attention, 50% cutoff has been used to come to these probability class, to these prediction classes. But anyway, since we have the probability of these data objects in the test set, now we can have a different cutoff point, right? So how about we have 0.75 as a new cutoff point? And when we do have a cutoff point larger than 0.5, we are preferring precision or specificity over sensitivity or recall, right? So we do that by this line of code. We say if it's larger than, if the case of yes, the probability is only when it's larger than 0.75, we want it to be yes, right? So we want less number of time yes, just as an example. So once we run this, our new classes are here. You can see that we have more often no, and if and only if we've got all the evidence that we need, which means that the probability is larger than 0.75, then we want it to be yes. But other than that, we want it to be no, right? So even for these cases that the probability was larger than 50%, now we are making decision of no. So now we do the confusion matrix for this new predictions, which is a little bit lopsided by intentionally by design. So we see what's going to be the difference. Once we do that, we do see that our specificity has increased, as we saw, because we don't have any false positive anymore, and we have switched those to here. Like, do you remember, if you increase or improve sensitivity, specificity decreases, and vice versa. So that's that. And last thing we are going to learn in this video is going to be how we would go about creating an ROC. We use ROC function. We give our actual data in the test set, and also we give the class probability, the probability, and then we create our ROC. Once we run this, we see that our ROC is almost perfect. And let me actually change something here. Let me actually do this. Let's see. So let's do this on the whole data instead of just the test set, right? So let me just do it on the whole data. Df no, because for a ROC we need way more data. So let's do it here. We need this. Let's see what happens. So we've got way more data. Now let's do an ROC. Oh, this has to change too. So this has to change too. All right, let's do this now. There we go. So now our ROC is more look like an ROC. There's like, you know, ups and downs here. So we do see that, you know, this is our ROC and like it's not perfect. But since the test set were just too small, our ROC seemed to be perfect. But our area under the curve is 0.915. Alright, so let's get back to the slide. We only actually have the summary to get to. So in this video we talked about what is KNN, and we saw the flaw of the KNN, which was, you know, it's not really scalable and it's going to be computationally expensive for larger data set. And then we talked about how we set K, and we saw everything we talked about in one simple example using our environment. Until the next video.